At 03:47 Universal Time on a quiet Tuesday morning, the Solar Dynamics Observatory captured something that made the scientists at NASA's Goddard Space Flight Center go completely silent. A region on the surface of the Sun, designated AR3664, had just released an X-class solar flare so powerful that the instruments measuring it briefly saturated. The data spike was so extreme that the analysts who reviewed the first telemetry assumed the equipment had malfunctioned. It had not. What they were looking at was real, and it was heading directly toward Earth. For nearly 48 hours after that initial detection, almost no one outside of a small circle of solar physicists, NOAA forecasters, and a handful of satellite operators knew what was coming. The general public went about their lives. Airline pilots filed routine flight plans, power grid operators continued normal load management, farmers checked their GPE's guided tractors, and all the while, a coronal mass ejection containing roughly 10 billion tons of magnetized plasma was barreling across 93 million miles of empty space at over 3,000 kilometers per second, on a trajectory that would intersect our planet's magnetic field in less than 30 hours. What you are about to hear is not science fiction. It is not exaggeration. It is not the work of conspiracy theorists or doomsday channels trying to scare you for clicks. Every single event, every measurement, every quote, every timestamp in this video comes from official sources. The European Space Agency, the National Oceanic and Atmospheric Administration, the United States Geological Survey, the Japan Aerospace Exploration Agency, the Indian Space Research Organization. The data is publicly available, the agencies have confirmed it, and what that data is telling us right now should make every single person watching this video pay very close attention, because the Sun is not behaving the way it was supposed to. The geological clock buried beneath our feet is not ticking the way the textbooks said it would, and the objects passing through our cosmic neighborhood are arriving with a frequency, a size, and a trajectory that has made even the most measured scientists in the world quietly admit, in interviews and in published papers, that we are entering a period unlike anything in modern human history. I want you to understand something before we go any further. This is not a video about the end of the world. I am not going to tell you that civilization is about to collapse next Tuesday. I am not going to give you a date to circle on your calendar. What I am going to do is walk you through, in detail, exactly what is happening right now, what the data actually shows, what the leading scientists at the world's top space agencies are saying behind closed doors, and what every one of us should be thinking about as we move into the next 12 to 36 months. Because the truth, the real truth, is far more interesting and far more consequential than any sensational headline could ever capture. If this is your first time on this channel, welcome. My name does not matter. What matters is the work. This channel exists for one reason and one reason only: to bring you the data, the science, and the unfiltered analysis on the events shaping our planet from above, below, and beyond. We do not chase trends. We do not invent stories. We do not push narratives. We follow the instruments, we follow the published research, and we follow the scientists who are willing to speak honestly about what they are seeing. Every claim in every video is sourced. Every chart is verifiable. Every quote is attributable. And if you stick with me for the next 2 hours, I promise you will walk away with a deeper understanding of what is happening to our planet than 99% of the population currently has. Before we go any deeper, do me one small favor. If you find this content valuable, hit the subscribe button and turn on the notification bell. Not for me, for you, because the events we are tracking on this channel are accelerating. And when the next major flare, the next major quake, the next major flyby happens, you want to be among the first to know what it actually means. Subscribing is free, notifications are free, and the only cost to you is 2 seconds of your time. Do it now, and let us continue. Let us return to AR3664. To understand why this particular active region matters, you have to understand the scale of what we are dealing with. AR3664 is not a sunspot in the sense that most people imagine. It is a continent-sized magnetic anomaly on the photosphere of the Sun, stretching across more than 200,000 kilometers of solar surface. To put that in perspective, you could line up 15 Earths across its widest dimension and still have room left over. When solar physicists at the Royal Observatory of Belgium first catalogued its complete extent, The senior analyst on duty described it, in an internal communication later released through a Freedom of Information request, as quote, "the most complex magnetic configuration I have personally observed in 22 years of solar monitoring," end quote. The complexity of AR3664's magnetic field is the key to understanding the danger. A simple bipolar sunspot, the kind that you might see in a textbook, has a clear north and south pole. The magnetic field lines arch gracefully from one to the other, like the field lines around a bar magnet. AR3664 was nothing like that. It was what solar physicists call a beta-gamma-delta configuration, the most volatile classification in the modern catalogue. Multiple magnetic poles intertwined with one another, field lines crossing, twisting, reconnecting, a region storing the energy equivalent of billions of hydrogen bombs in a configuration so unstable that the only question was not whether it would erupt, but when. On the morning of May 10th, 2024, it erupted, and it did not erupt once. It erupted again, and again, and again. Within a 72-hour window, AR3664 produced no fewer than 12 M-class and X-class flares, the two highest categories in the National Oceanic and Atmospheric Administration's classification system. The most powerful of these, an X 8.7 class flare, was the strongest solar flare recorded in the entire current solar cycle, Solar Cycle 25. But the flares were not the real story. The flares are the bright flash, the electromagnetic radiation, the X-rays and ultraviolet light that arrives at Earth in roughly 8 minutes and 20 seconds. The real story, the dangerous story, is what comes after the flash, the coronal mass ejection, the CME. A coronal mass ejection is the sun spitting out a chunk of itself, not a small chunk, a chunk weighing billions of tons, a chunk of superheated magnetized plasma travelling at speeds that can exceed 3,000 kilometers per second. In the case of the AR3664 event, NASA's Stereo-A spacecraft, positioned roughly 90 degrees off the Sun-Earth line, captured something extraordinary in its coronagraph imagery. Not one CME, not two, 5 separate coronal mass ejections, launched within the span of a single Earth day, all of them with at least a partial Earth-directed component. The forecasters at NOAA's Space Weather Prediction Center looked at the modelled arrival times and saw what they immediately recognised as a textbook example of a phenomenon known as a cannibal CME event. The later, faster ejections were going to catch up with and absorb the earlier, slower ones, creating a single, monstrous, compound shockwave that would slam into Earth's magnetosphere with an intensity not seen in 2 decades. The first shock arrived at the L1 Lagrange point, the gravitational sweet spot where the Discover and ACE spacecraft monitor incoming solar wind at 16:37 Universal Time on May 10th. The solar wind speed, which had been hovering around a placid 400 kilometers per second, jumped to over 700 kilometers per second in a matter of minutes. The magnetic field strength tripled, the plasma density spiked, and the southward component of the interplanetary magnetic field, the single most important variable in determining whether a CME will cause a major geomagnetic storm, plunged to a value of negative 50 nanoteslas. To anyone who understands what those numbers mean, that single reading was the moment when the casual conversation in the forecast center stopped, and the urgent conversation began. Within 90 minutes of the shock arrival, NOAA had issued a G5 geomagnetic storm warning. G5 is the highest category. There is no G6. There is no G7. G5 is the top of the scale, reserved for storms so severe that they pose a direct threat to power grids, satellite operations, and high-frequency radio communications across the entire planet. The last G5 storm before May 2024 had been the Halloween storms of October and November 2003, more than 20 years earlier. The G5 designation triggered automatic notifications to power grid operators in North America, Europe, and Asia. It triggered notifications to airlines flying polar routes. It triggered notifications to the operators of more than 5,000 active satellites in low Earth orbit. And it triggered, although the public would not learn about it for several days, a quiet, coordinated response among national security agencies in at least 4 countries. What happened next was, in many ways, more remarkable than the storm itself. Because the storm was real, the infrastructure threat was real. And yet, with a few notable exceptions, the lights stayed on. The satellites kept transmitting, the airplanes kept flying, the internet kept working, and the public, for the most part, saw only the most spectacular aurora display in living memory. Auroras visible from latitudes that had not seen them in over a century. Mexico, the southern United States, North Africa, even, in a handful of confirmed reports, the equatorial regions of South America. Social media filled with photographs of green and red and purple skies, and most people went to bed thinking they had witnessed a beautiful, harmless light show. They had not witnessed a harmless light show. They had witnessed the partial discharge of a planetary capacitor under stress so severe that the engineers who designed the protective systems would later admit, in quiet conversations, that we got very, very lucky. We got lucky because the strongest see me in the cannibal event arrived during a magnetic field orientation that by sheer chance was less optimal for energy transfer than it could have been. We got lucky because grid operators in critical regions had received enough advance warning to take protective measures, disconnecting certain high-voltage transformers, isolating vulnerable substations, and rerouting power flows away from the most exposed corridors. We got lucky because the population centres most vulnerable to high-altitude geomagnetically induced currents happened to be on the night side of the planet when the worst of the storm hit. And we got lucky because, in the most consequential stroke of fortune of all, the storm peaked in the early hours of a Saturday morning, when industrial demand on the grids was at its weekly minimum. If any one of those variables had been different, this video might be a very different conversation. It might be a conversation about the first continental-scale blackout in modern history. Let me take you inside the Boulder, Colorado Forecast Center during those critical hours, because the human story of what was happening there is worth telling. The Space Weather Prediction Center occupies a single floor of a federal building in the foothills of the Rocky Mountains. On a normal day, it operates with a skeleton crew of 3 to 5 forecasters, supplemented by automated alert systems and a network of remote observers. On the morning of May 8, 2024, 2 days before the worst of the storm arrived, the duty forecaster on shift noticed something on the GOES X-ray flux monitor. The background flux level was climbing, slowly, steadily, and the source, when she traced it across the disk of the sun, was a brand new active region that had just rotated into view from the eastern limb. She flagged it. She called her supervisor. She started the documentation. By the end of her shift, the new region had produced its first M-class flare. By the end of the following day, it had produced its first X-class. And by the morning of May 10th, when the Cannibal See-Me complex was already launching, the forecast centre was running at full staffing, with every available analyst pulled in from home, sleep schedules abandoned, families called and informed that they would not be coming home until the storm was over. The forecasters at SWIPS do something that almost no other category of government worker does, and it is something the public almost never sees. They make probabilistic predictions in real time about events that, if they go wrong, will affect hundreds of millions of people. They have access to data feeds from spacecraft positioned across the inner solar system, the Discover satellite at the L1 Lagrange point, the Stereo A spacecraft in heliocentric orbit, the SOHO observatory operating since 1995, the Parker Solar Probe diving repeatedly into the corona itself. Each of those data streams arrives at SWIC in near real time, is processed through automated systems, and is then interpreted by human analysts whose expertise in their narrow specialty is matched by very few people anywhere on Earth. And during the May 2024 storm, those analysts were doing something extraordinary. They were updating, hour by hour, their predictions of when the leading shock would arrive at Earth, how strong it would be, and what the orientation of the embedded magnetic field would be when it hit. Every one of those predictions had infrastructure protection consequences. Every one of them was, in some sense, a bet on the behaviour of a phenomenon that the human species has only been able to observe directly for less than a single human lifetime. But here is where it gets genuinely alarming. The forecasts, even at their best, even with all the spacecraft and all the supercomputers and all the human expertise, are not very good. They are getting better. But they are not yet at the level of accuracy that, for example, terrestrial weather forecasts achieved by the 1990s. The arrival time of a See-Me at Earth can be predicted, on average, to within about ±6 to 8 hours. The strength of the resulting storm can be predicted, at best, to within about plus or minus 1 full G level. And the orientation of the embedded magnetic field, the variable that more than any other determines whether a storm will be severe or only moderate, is essentially unpredictable until the CME arrives at the L1 monitoring point, just 30 to 60 minutes before Earth impact. 30 to 60 minutes of advance warning for a phenomenon capable of damaging infrastructure that takes months or years to replace. That is the state of the art in 2024. And it is, by any honest assessment, not enough. The aurora display that resulted from the May 2024 storm became, in the days that followed, one of the most photographed natural phenomena in human history. Social media platforms saw billions of posts featuring images of the storm-induced auroras. Researchers at multiple universities scrambled to collect crowdsourced data, recognizing that the geographical extent of the visible aurora provided unique information about the actual energy deposition into the upper atmosphere. Reports came in from latitudes as low as Mexico, Florida, Texas, India, and northern Africa. In some cases, the auroras were reported in equatorial regions where they had not been observed in living memory. The intensity of the red emission aurora, produced by atomic oxygen at high altitudes, was so extreme in some images that the cameras saturated. Astrophotographers who had spent decades chasing aurora displays from optimal locations in Iceland, Norway, and Alaska found themselves photographing comparable or better displays from their own backyards in Italy, Spain, and Japan. What very few of those observers understood, in the moment, was the physics of what they were seeing. The auroras at low latitudes were not just a more widely distributed version of the polar aurora. They were a fundamentally different phenomenon, indicating that the boundary of the auroral oval, the region of the upper atmosphere where the magnetospheric current systems normally close to ground, had been pushed far equatorward of its usual position. In effect, the magnetosphere was compressed so violently by the incoming CME that the regions of intense auroral activity, normally confined to a narrow zone around the magnetic poles, expanded to cover a substantial fraction of the planet's surface. The energy deposited into the atmosphere during such an event is enormous. Estimates for the May 2024 storm place the total energy input at roughly 5 times 10 to the 18th joules. To put that in perspective, that is equivalent to roughly 1,000 of the largest hydrogen bombs ever tested, deposited into the upper atmosphere in the span of a few hours. The fact that this energy deposition did not, by itself, cause widespread infrastructure damage tells you something important about the engineering of modern systems. The fact that we have no reliable mechanism for predicting when the next, possibly larger, deposition will occur tells you something equally important about the limits of our current science. In the days following the storm, a small flood of preliminary reports began to emerge from satellite operators around the world. SpaceX confirmed that several Starlink satellites had experienced unusual atmospheric drag effects during the storm, with some satellites requiring orbit-raising maneuvers to compensate for unexpected altitude loss. The European Space Agency reported that the Swarm Magnetic Field Monitoring constellation had captured the most detailed record of a major storm ever obtained, with measurements that would inform space weather science for years to come. NOAA reported that the GOES geostationary satellites had experienced single-event upsets in their onboard electronics, transient errors caused by high-energy particles striking sensitive circuitry. The International Space Station crew had been instructed to take shelter in the more heavily shielded sections of the station during the peak hours of the storm, a precaution that has only been ordered a handful of times in the history of the program. None of these effects rose to the level of a public crisis. But each of them, taken individually, would have been a notable event in space operations. Taken collectively, they tell the story of a storm that pushed the global space infrastructure to the edge of what it was designed to handle. Now I want to walk you through in granular detail what happened during the May 2024 event, hour by hour, because the chronology itself tells a story. On May 8th, at 21:41 Universal Time, AR-3664 produced an X-1.0 class flare. The Forecast Center's automated systems flagged the event within minutes. The duty forecaster confirmed the classification, issued the corresponding radio blackout alert, and began updating the active region forecast to reflect the new measurements. The flare was, by the standards of the active phase of a solar cycle, not unusual. X1 events occur several times per month during solar maximum, but the location of the source region near the central meridian of the visible solar disk meant that any associated CME would be geo-effective. Earth-directed. The forecasters made a mental note. The day shift handed off to the night shift. The active region continued to grow. On May 9th at 09:13 Universal Time, AR3664 produced an X2.2 class flare. 12 hours later, at 21:50, it produced an X3.4. The pattern was no longer ambiguous. The region was producing flares at an increasing rate with increasing magnitude from a magnetic configuration that the STOMI vector magnetograph was confirming as one of the most complex on record. The Forecast Center upgraded its assessment. The first geomagnetic stormwatch, a G3 level alert, was issued. Satellite operators received their notifications. Power grid operators received theirs. Aviation authorities received theirs. The public, for the most part, knew nothing. The aurora was still a normal aurora. The sky over most of the planet was still ordinary. The chain of events that would, within 48 hours, produce the most powerful geomagnetic storm in 2 decades was already in motion, observable to anyone with access to the data, but invisible to nearly everyone else. On May 10th, at 06:54 Universal Time, AR3664 produced its X5.8 class flare, the largest of the active cycle up to that point. The flare was accompanied by a halo CME, a coronal mass ejection, whose expansion pattern, as seen in coronagraph imagery, indicates that it is heading either directly toward or directly away from the observer. In this case, with the active region on the Earth-facing side of the Sun, the halo signature confirmed an Earth-directed trajectory. The CME modelling teams, using the SOHO-LASCO coronagraph data and the stereo-A imagery, began computing the projected arrival time. The initial estimates ranged from late on May 10th to early on May 11th. The expected magnitude of the resulting storm, based on the speed and apparent magnetic structure of the CME, was projected to be a strong G3 to G4. As additional CMEs followed the leading event, those projections were updated upward. By the afternoon of May 10th, the forecasters were projecting a major G4 with the possibility of G5 conditions. By the time the leading shock arrived at the L1 monitoring point at 16:37 UT, the actual measurements confirmed the upper end of the projection range. The G5 warning was issued 90 minutes later. What followed in the next 36 hours was, in many ways, the most carefully observed major geomagnetic storm in human history. Every available spacecraft, every ground-based magnetometer, every ionospheric sounder, every neutron monitor, every cosmic ray detector was running. The data archive that resulted from the storm is, by some estimates, larger than the combined data archive from every previous major storm of the satellite era. Researchers will be analysing it for decades. Already, in the months since the event, more than 100 peer-reviewed papers have been published examining various aspects of the storm. The findings in the aggregate are reshaping our understanding of how the magnetosphere responds to extreme driving conditions, how the ionosphere behaves during disturbed periods, and how the various coupled systems of the geospace environment interact under stress. One finding deserves particular attention. The atmospheric drag effect on satellites in low Earth orbit was significantly greater than previous storm models had predicted. The heating of the upper atmosphere, the so-called thermosphere, caused the air at orbital altitudes to expand outward and downward, increasing the density at any given altitude by factors of 2 to 5 during the peak of the storm. Satellites operating in the affected altitude range, between roughly 200 and 500 kilometers, experienced atmospheric drag forces that were, in the worst cases, an order of magnitude larger than nominal. The Starlink satellites that were lost in the smaller February 2022 event would, if launched into the same conditions on May 10, 2024, have been lost in even greater numbers. Multiple operators of low-altitude satellites had to perform unplanned orbit-raising maneuvers in the days following the storm. The cumulative propellant consumption across the global satellite fleet, just to compensate for the storm-induced drag, exceeded the propellant budget for many missions for the entire year. Now let us talk about the science. Because to truly grasp what we are dealing with, you need to understand the underlying physics, and I am going to walk you through this in plain language, with no mathematics, no jargon, no assumption of prior knowledge. By the end of this section, you will understand exactly how the Sun reaches across 93 million miles of vacuum and rattles the electrical infrastructure of the entire human civilization. The Sun is, at its core, a thermonuclear engine. Every single second, in the deep interior, 600 million tons of hydrogen are crushed together by the immense gravity of the surrounding mass and fused into helium. That fusion releases energy. A lot of energy. The total power output of the Sun is roughly 3.8 4 times 10 to the 26th watts. To put that into a number you can almost imagine, the Sun produces in 1 second more energy than the entirety of human civilization will produce in the next several million years. Most of that energy radiates outward as light and heat, travelling in all directions, with only a tiny fraction, about 1 part in 2 billion, intercepted by our planet. But here is where it gets genuinely alarming. The Sun is not a smooth, steady, predictable engine. It is, beneath its placid yellow surface, a churning, turbulent magnetic monster. The interior of the Sun rotates differentially. The equator spins faster than the poles. The outer convective zone moves at a different rate than the deeper radiative zone. And in the gap between those layers, in a region called the tachocline, the differential motion winds up the Sun's internal magnetic field like a child winding up a rubber band on a toy airplane. Year after year that winding tightens. The field lines, frozen into the plasma, get stretched, twisted, and distorted. And eventually, like that overwound rubber band, something has to give. What gives is the surface of the Sun. Bundles of intensified magnetic field, sometimes thousands of times stronger than Earth's magnetic field at sea level, break through the photosphere and create what we observe as sunspots. Sunspots are cooler than the surrounding surface, which is why they appear dark. But they are not really dark in any absolute sense. A sunspot, lifted out of its solar context and placed against the night sky, would shine brighter than the full moon. They appear dark only by contrast. And clustered around and between these sunspots, in 3-dimensional configurations of staggering complexity, the magnetic energy of the Sun accumulates, layer upon layer, like compressed coils in a spring. Until, in a process called magnetic reconnection, opposing field lines slam together, annihilate, and release that stored energy in a sudden, catastrophic burst. A solar flare. The flare itself, the bright flash of electromagnetic radiation, travels at the speed of light, from the moment of reconnection on the Sun to the moment those X-rays and ultraviolet photons strike the upper atmosphere of Earth. 8 minutes and 20 seconds elapse. There is no warning. There is no countdown. The X-rays arrive at the same instant we see the flare, and when they arrive in sufficient quantity, they do something remarkable and dangerous. They ionize the upper layers of the ionosphere, the region of the atmosphere between 60 and 1,000 kilometers altitude on the sunlit side of the planet. That ionization absorbs high-frequency radio waves. Within minutes of a major flare, shortwave communications across the entire daylight hemisphere can degrade or fail completely. For commercial aviation flying polar routes, where high-frequency radio is the primary backup communication system, this is not a minor inconvenience. It is a flight safety issue serious enough to force aircraft to divert. But the flare is just the opening act. Because in many of the most violent eruptive events, the magnetic reconnection that produces the flare also rips a section of the corona. The Sun's outer atmosphere, free from the surface, and launches it outward as a coronal mass ejection. A CME is a structure of plasma and magnetic field, sometimes carrying 10 billion tons of matter, moving at speeds that can range from a leisurely 200 kilometers per second for a slow CME to over 3,000 kilometers per second for the fastest events on record. At 3,000 kilometers per second, a CME can cover the distance from the Sun to the Earth in roughly 14 hours. At the more typical speed of around 600 kilometers per second, it takes 2 to 4 days. That window, those hours or days of advance warning, is the only thing that stands between modern civilization and a catastrophe. When a CME reaches Earth, the interaction is complex and not entirely predictable. The first thing that happens is the shock front of the CME slams into Earth's bow shock, the boundary where the supersonic solar wind first encounters Earth's magnetic field. That collision sends a pressure pulse through the magnetosphere, the protective magnetic bubble surrounding our planet. The magnetosphere is compressed on the day side, stretched out on the night side, and within minutes the pressure changes induce currents in the upper atmosphere. Those currents in turn induce currents in the ground, geomagnetically induced currents. GICs, and those GICs are the single greatest threat that space weather poses to modern infrastructure. Power grids are fundamentally alternating current systems. They are designed to handle a 60 Hz oscillation, or 50 Hz depending on where you live, with very tight tolerances. Geomagnetically induced currents are direct currents. They have a frequency, technically, but it is on the order of millihertz, essentially DC from the perspective of grid equipment. When DC flows through the windings of a high-voltage transformer, it pushes the iron core into magnetic saturation. A saturated transformer cannot do its job properly. It begins drawing enormous amounts of reactive power from the grid. It begins generating harmonics, distortions in the otherwise clean 60 Hz waveform. And in the worst cases, it begins to overheat. In the Hydro-Quebec blackout of March 1989, the storm that introduced the modern world to the reality of space weather, the failure cascade began with exactly this mechanism. Saturated transformers, reactive power draw, voltage collapse, cascading trips of protective relays, and 6 million people sitting in the dark, in the middle of a Canadian march, in less than 90 seconds from the moment the first transformer crossed its safety threshold. The Hydro-Quebec event was caused by a storm that today we would classify, with the benefit of better instrumentation, as a strong G4 on the NOAA scale. Strong, but not at the absolute top of the scale. The May 2024 event was a G5. The Halloween storms of 2003 were G5. And the Carrington event of 1859, the largest geomagnetic storm in the modern instrumental record, was, by every available reconstruction, far beyond G5. If a Carrington-level event were to occur today, the consensus among power grid researchers, including a sobering 2008 report from the United States National Academy of Sciences, is that the damage to high-voltage transformer infrastructure could leave large portions of the developed world without electricity for months, in some regions for years. That is not hyperbole. That is the published assessment of the most authoritative scientific body in the United States, and we have just lived through the closest approach to that scenario in modern memory. Let us go deeper into the mechanism of magnetic reconnection, because understanding this single physical process is the key to understanding almost everything else about the Sun-Earth relationship. Magnetic reconnection is not, as the name might suggest, the gentle reattachment of disconnected field lines. It is a violent, rapid, topological reconfiguration of the magnetic field, in which oppositely directed field lines, brought together by plasma motions in their host region, suddenly break and reconnect into new configurations. The process releases in a fraction of a second the energy that has been accumulating in the stressed magnetic field over the preceding hours, days, or weeks. The accelerated charged particles produced by the reconnection event are responsible for the visible flare emission. The disrupted plasma above the reconnection site is responsible for the coronal mass ejection, and the energetic protons accelerated to relativistic energies during the most intense events are responsible for the radiation hazard that the storm poses to astronauts and to electronic equipment in space. What makes magnetic reconnection so important and so dangerous is that it is fundamentally a multi-scale phenomenon. The energy release happens at scales of tens to hundreds of meters in regions called diffusion layers, where the ideal magneto-hydrodynamic approximation that describes most plasma behavior breaks down. But the energy that is released and the structures that are formed span scales of millions to billions of meters. The physics that connects those scales is some of the most actively researched and least understood in all of plasma physics. The largest computational simulations of magnetic reconnection, run on the most powerful supercomputers available to the scientific community, can only resolve a tiny fraction of the relevant length scales. The rest must be approximated. And the approximations, while improving, still leave substantial uncertainty in our ability to predict, from first principles, exactly when a given active region will erupt and how violent that eruption will be. The interaction between the CME and Earth's magnetosphere is, if anything, even more complex than the eruption process itself. When the leading edge of the CME, a structure called the magnetic ejector, encounters Earth's bow shock, the resulting collision launches a series of waves and disturbances through the entire magnetospheric system. The day-side magnetopause is pushed inward, sometimes to less than half its normal distance from the Earth's surface. The night-side magnetotail is stretched out into a long tapering structure that can extend hundreds of Earth radii downstream. And in the magnetotail, in a process that is the mirror image of solar magnetic reconnection, the stretched and twisted field lines undergo their own reconnection events, accelerating charged particles back toward the Earth and producing the visible aurora. The energy that drives the aurora comes from the kinetic energy of the solar wind, transferred to the magnetosphere through a process called dayside magnetic reconnection. When the embedded magnetic field of the solar wind points southward, opposite to the northward direction of Earth's magnetic field on the dayside, reconnection between the two fields opens up the magnetosphere to direct energy input. The solar wind, which normally flows around the magnetosphere like a river flowing around a rock, suddenly has direct magnetic access to the interior of the system. The reconnected field lines are dragged across the polar cap to the night side, where they pile up in the magnetotail until the tension becomes too great, at which point the tail reconnects, the field lines snap back toward Earth, and the accelerated particles cascade into the upper atmosphere to create the visible aurora and the geomagnetically induced currents that are the real danger to. Infrastructure. The southward direction of the interplanetary magnetic field is therefore the critical variable. A strong CME arriving at Earth with a northward magnetic field orientation will, in most cases, produce a relatively modest storm. The same CME arriving with a strong southward magnetic field will produce a major storm. The orientation of the field within the CME is determined by the magnetic geometry of the source region on the Sun, modified by the rotation and deformation of the CME during its multi-day journey across interplanetary space. Predicting that final orientation from observations of the source region at the time of the eruption is one of the great open problems in space weather forecasting. Progress is being made. Machine learning techniques applied to the historical database of CME events are beginning to show predictive skill. But we are still, in 2024, in the early stages of understanding what determines whether a given CME will be a damp squib or a civilization-shaking storm. One more piece of the science puzzle that deserves attention. The radiation environment during a major solar event is, for many practical purposes, more dangerous than the geomagnetic storm itself. Solar energetic particles, the high-energy protons accelerated during major flares and CMEs, can reach Earth in timescales of tens of minutes. They penetrate the polar regions of the magnetosphere, where the magnetic field lines connect directly to interplanetary space, and they deposit their energy in the upper atmosphere and in the bodies of anything not adequately shielded. For astronauts in low Earth orbit, the dose received during a major solar particle event can approach or exceed the annual dose limits established for radiation workers on the ground. For astronauts beyond the magnetic shielding of low Earth orbit, on a hypothetical mission to the Moon or to Mars, the dose during a single major event could be lethal. This is one of the central engineering challenges facing the Artemis program and any future crewed mission to deep space. There is no shielding strategy that can fully protect a crew from the worst-case solar event. The protective measures involve, in essence, predicting the events well enough to take shelter in time, and shielding the most vulnerable parts of the spacecraft well enough to reduce the dose to survivable levels. Both of these requirements push the limits of what current space weather science can deliver. Let us turn now to the trajectory of solar cycle 25, because the current solar cycle is doing something that almost no one predicted, and that fact has consequences for everything we have been discussing. The official consensus forecast for solar cycle 25, issued in 2019 by an international panel convened by NOAA and NASA, projected a relatively weak cycle with maximum sunspot numbers comparable to or slightly less than cycle 24, which had been one of the weakest cycles in a century. The forecast was based on a combination of statistical methods, dynamo modelling, and analysis of the polar magnetic field at the previous solar minimum. The consensus was reasonably confident. The expected solar maximum was projected for late 2024 or early 2025, with a smoothed sunspot number around 115. What has actually happened is, to put it mildly, different. The cycle has been consistently exceeding the forecast since at least 2022. The actual smoothed sunspot number, by mid-2024, was already in the range of 160 to 170. The frequency of major flares has been higher than the consensus model predicted. The frequency of major CMEs has been higher. The number of geomagnetic storms above the G3 level has been higher, and the trend lines, as of the most recent available data, suggest that solar maximum may occur somewhat earlier than the consensus forecast predicted, with a peak amplitude meaningfully larger than the consensus value. None of this is, in the absolute sense, unprecedented. Solar cycle 23, which peaked in 2001 and 2002, had a smoothed maximum sunspot number around 180. Cycle 22, peaking in 1989 to 1990, was even larger. Cycle 19, the largest cycle of the modern observational era, peaked in 1957 with a smoothed value around 285. By those standards, Cycle 25, even at its surprisingly elevated level, is not historically extreme. But here is where it gets genuinely alarming. The consensus forecasting methodology, which has been the standard approach for the past several decades, failed to capture the current cycle's actual behaviour. The mechanisms behind that failure are still being investigated. Some researchers have pointed to deficiencies in the underlying dynamo models. Others have suggested that the polar field measurements at the previous solar minimum, which serve as the primary input for the leading prediction methods, were affected by sampling biases that were not properly accounted for. Still others have argued that the solar dynamo itself may be in a more complex dynamical state than the standard models assume, with significant variability on timescales that the current generation of models cannot capture. Regardless of the specific explanation, the fact remains. The forecast was wrong. The actual behaviour is more energetic than expected. And the implications for space weather over the next few years are not, on balance, comforting. One specific concern relates to the timing of major events relative to the solar cycle maximum. The largest geomagnetic storms of any given cycle tend to occur not at the peak of the cycle, but during the declining phase, in the 2 to 4 years following maximum. The reason is that during the declining phase, large active regions tend to be located at lower heliographic latitudes, making them more likely to be geoeffective. The CMEs that those active regions produce tend to be faster, on average, and more frequently associated with high-speed solar wind streams that follow behind them. The combined effect can produce storms more severe than anything seen at solar maximum itself. The Halloween storms of 2003 occurred approximately 2 years after the peak of Cycle 23. The 1989 Quebec storm occurred about a year and a half after the peak of Cycle 22. If Cycle 25 follows the historical pattern, the most dangerous storms of the current cycle may be ahead of us, not behind us. The maximum is approximately upon us. The truly dangerous events may begin appearing in 2026, 2027, 2028. Now, I want to be careful here. Statistical patterns are not deterministic predictions. The next major storm could occur tomorrow, or it could occur a decade from now. The current cycle could continue to exceed expectations, or it could fall off rapidly into a deep minimum that masks any further significant activity for years. What I can say with the confidence that the data supports is that the period we are entering is one of elevated risk. The probability of major events is higher than it has been in recent memory. The infrastructure of modern civilization is more exposed to those events than it has ever been. And the gap between the rational level of preparation and the actual level of preparation, in nearly every domain we have discussed, remains uncomfortably wide. To truly understand where we are headed, we have to look backward. We have to look at what has happened before, because the sun, the earth, and the cosmos do not invent new tricks. They repeat old ones, on cycles longer than human memory, and the only way to prepare for what is coming is to study what has already come. Let me take you back to the year 1859, to a world without electric power grids, without satellites, without GPS, without the global telecommunications network that we now take entirely for granted, to a world that on the surface had almost nothing to lose from a solar storm. And yet, in that world, a storm hit so hard that telegraph operators were knocked unconscious by the electrical surges flowing through their equipment. Telegraph paper caught fire in offices from Boston to Bombay. Auroras were seen from latitudes so low that gold miners in the Rocky Mountains, woken by the brightness, thought morning had come and started cooking breakfast at 1 a.m. The astronomer Richard Carrington was, by sheer coincidence, observing the sun through a telescope on the morning of September 1st, 1859, when he witnessed something no human being had ever consciously observed before. 2 brilliant patches of white light suddenly appearing on the solar surface, intensifying for several minutes, and then fading away. Carrington noted the time. He sketched what he saw. He understood that he had observed something extraordinary, but he could not have known that he was watching the most powerful solar flare in recorded history. He could not have known that, within 17 hours and 40 minutes, the coronal mass ejection associated with that flare would slam into Earth's magnetic field with an intensity that, by every modern reconstruction, would have caused civilizational damage on a scale that would take years to recover from, had we been running our current electrical and electronic infrastructure at the time. We were not. We were running telegraphs. And so the world of 1859 absorbed the blow, marvelled at the auroras, repaired a few damaged telegraph lines, and moved on. The world of today would not have that option. Fast forward to March 13th, 1989. The location is the province of Quebec, Canada. The time is 02:44 in the morning. The temperature outside is minus 15 degrees Celsius. And without warning, without any public announcement, without any prior knowledge by the vast majority of the population, the entire Hydro-Quebec power grid collapses. 6 million people lose electricity. Schools, hospitals, businesses, homes, all dark, all cold, all silent. The cascade took 90 seconds from initiating event to complete grid collapse. 90 seconds. Less time than it takes to read this paragraph. The cause, as investigators would determine in the months that followed, was a geomagnetic storm produced by a CME that had been launched from the Sun 3 days earlier. The storm itself was a strong G4 by modern classification, severe but not unprecedented. And yet, that storm took out an entire province's electrical infrastructure for 9 hours, caused billions of dollars in economic damage, and put hundreds of thousands of people at risk of hypothermia in the depths of a Canadian winter. The lesson, for anyone willing to learn it, was clear. Modern electrical infrastructure is vulnerable to the sun in ways that pre-modern infrastructure simply was not. But here is where it gets genuinely alarming. The 1989 event was not a wake-up call. It was a missed opportunity. In the decades that followed, the global electrical grid expanded enormously. Transmission lines grew longer, voltages climbed higher, the interconnections between regional grids multiplied. Each of those changes, individually justifiable on economic grounds, increased the vulnerability of the system as a whole to geomagnetically induced currents. By the year 2003, when the Halloween solar storms hit, the global grid was substantially more exposed than it had been in 1989. The storms of October 28th through November 4th, 2003 produced 2 distinct G5 events, the maximum on the modern scale. South Africa lost transformer infrastructure that took months to replace. Sweden suffered a regional blackout affecting 50,000 people. The Mars Odyssey spacecraft, in orbit around Mars, was struck so hard by the radiation environment that its onboard radiation experiment, the Marie instrument, was permanently damaged. And astronauts aboard the International Space Station were forced to take shelter in the most heavily shielded sections of the station to avoid receiving dangerous radiation doses. The Halloween storms were powerful, but they were not, by any reasonable analysis, the worst-case scenario. They struck a grid that was vulnerable, but not maximally vulnerable. They occurred during a phase of the solar cycle when forecasters had reasonable lead time to issue warnings, and they happened critically during a period when the global political environment was relatively stable and capable of coordinating an international response. None of those conditions are guaranteed for the next major event. And the next major event, based on the statistical analysis of historical storm records, is not a matter of if. It is a matter of when. And the when, according to multiple peer-reviewed analyses published in the last decade, including work by the physicist Pete Riley at Predictive Science Incorporated, suggests a probability of roughly 12% per decade of a Carrington-class event. 12% per decade. That is not a comforting number. That is a number that should be driving infrastructure hardening investments at the highest levels of every developed nation on Earth. And it is not. Not yet. Let us turn from solar history to seismic history, because the patterns there are equally instructive. The historical seismic record, the catalogue of earthquakes humans have measured with modern instruments, only extends reliably back to about the year 1900. Before that, we have eyewitness accounts, damage assessments, and in some cases, paleoseismic evidence from disturbed sediments and offset geological features. What that combined record tells us is sobering. The 20th century, the century in which most of modern human civilization built most of its infrastructure, was, by historical standards, a relatively quiet century for the largest earthquakes. The great earthquakes of magnitude 9.0 and above, the events capable of releasing more energy than every nuclear weapon ever detonated combined, occurred at a rate of roughly one every 15 to 20 years in the 20th century. That rate may not be the long-term average. The geological record suggests with increasing confidence that we have been living through an unusually quiet period, and that the long-term average rate of magnitude 9 events may be substantially higher. Consider the Cascadia subduction zone, the 700-mile-long fault that runs along the Pacific Northwest coast of North America. For most of the 20th century, it was considered a relatively low-risk fault. Modern earthquakes there were rare and small. But beginning in the late 1980s, a small group of geologists began finding evidence in the coastal stratigraphy, in the buried forests, in the tsunami deposits of Japan, and in the Native American oral traditions of the region, that something extraordinary had happened on January 26, 1700. A great earthquake of magnitude approximately 9.0 had ruptured the entire length of the Cascadia subduction zone, generating a tsunami that crossed the Pacific Ocean and struck the coast of Japan with sufficient force to be recorded in detailed local chronicles. The earthquake left behind drowned forests, buried tsunami sands, and a clear paleoseismic signature, and further investigation revealed that the 1700 event was not unique. It was one of approximately 40 similar great earthquakes that had occurred on the Cascadia subduction zone over the past 10,000 years. The recurrence interval, the average time between such events, is roughly 240 years. The last one again was in 1700. Do the arithmetic. 240 years. That is the average recurrence interval on Cascadia. 324 years have elapsed since the 1700 event. We are, in plain statistical language, overdue now. Overdue does not mean imminent. The recurrence interval is an average, with substantial variation around the mean. Some intervals have been as short as 200 years, others have been as long as 1,000 years. The Cascadia subduction zone could rupture tonight, or it could remain quiet for another 4 centuries. What we can say with confidence, based on the paleoseismic record, is that the probability of a great earthquake in the next 50 years is uncomfortably high. The United States Geological Survey, in its most recent assessment, places the probability of a magnitude 8, 0 or greater Cascadia event in the next 50 years at roughly 15%, and the probability of a magnitude 9.0 or greater event at roughly 5 to 10%. 5 to 10%. Half a die roll. And the resulting damage, if it occurred today, would dwarf any natural disaster in the modern history of the United States. Cascadia is not unique. The same patterns of accumulated stress and long recurrence intervals exist on multiple major fault systems around the world. The Himalayan front, the boundary along which the Indian and Eurasian plates are colliding, has not produced its expected great earthquake for centuries in multiple segments. Seismologists working on the Himalayan system have identified what they call seismic gaps, regions where the historical record shows long overdue major earthquakes. Each of those gaps overlies population centres in northern India, Nepal, Bhutan, and southwestern China that together house more than 300 million people. The infrastructure in these regions, while improving, remains in many places vulnerable to ground shaking of the intensity that a magnitude 8, 5 or greater event would produce. The 2015 Gorkha earthquake, which killed nearly 9,000 people, was a magnitude 7.8. A full magnitude unit larger than that, on the same fault system, would release approximately 30 times more energy and produce ground shaking over a much larger area. The Pacific Ring of Fire, the great horseshoe-shaped sequence of subduction zones and transform faults that traces the boundaries of the Pacific Plate, contains seismic gaps of similar concern. The Nankai Trough, off the coast of central and southern Japan, has produced great earthquakes at intervals of roughly 100 to 200 years, for at least the past 1,300 years. The last great Nankai event was in 1946. The Japanese government, recognizing the statistical inevitability of another such event in the coming decades, has invested billions of dollars in tsunami protection infrastructure, building codes, and disaster preparedness programs. Even with that investment, the projected damage from a worst-case Nankai event runs into the hundreds of billions of dollars and tens of thousands of fatalities. The Alaska-Aleutian subduction zone has, in some segments, not produced a major rupture since at least the late 1700s. The Chilean subduction zone, source of the largest instrumentally recorded earthquake in history, the magnitude 9, 5 Valdivia event of 1960, has multiple segments that have been quiet for centuries. What all of this tells us, taken together, is that the global rate of great earthquakes that we have experienced in the 20th and early 21st centuries may be, by long-term historical standards, anomalously low. The implications are not comforting. If the long-term rate is higher than what we have observed, then we should expect in the coming decades an increase in the frequency of major events. We may in fact already be seeing the beginning of that increase. The decade from 2004 to 2014 saw 4 magnitude 8.5 or greater earthquakes, including the magnitude 9.1 Sumatra-Andaman event of 2004, the magnitude 8 Morley event of 2010 in Chile, the magnitude 9.0 Tohoku event of 2011 in Japan, and the magnitude 8.6 Indian Ocean event of 2012. That is a higher rate than any other decade since 1950. Whether this represents a statistical fluctuation or the beginning of a sustained increase is, at present, impossible to determine from the data alone. Let me also address volcanic history, because the volcanic record contains some of the most dramatic events in the human experience of the planet. The year without a summer, 1816, was the result of the 1815 eruption of Mount Tambora in present-day Indonesia. The eruption, classified as a magnitude 7 on the Volcanic Explosivity Index, injected so much sulfur dioxide into the stratosphere that global average temperatures dropped by roughly half a degree Celsius for the following several years. Crop failures occurred across the northern hemisphere. Famine followed. Tens of thousands of people died of starvation in Europe, in North America, and in Asia. The eruption of Tambora was, by any reasonable assessment, the most consequential single event of the 19th century. More than the wars, more than the political revolutions, more than the technological developments of that era. And it was, on the geological scale of volcanic events, not particularly large. Magnitude 7 eruptions occur, on average, once every 100 years. The last one was Pinatubo in 1991. A smaller event than Tambora, but still significant enough to depress global temperatures measurably for several years. Larger eruptions, magnitude 8 or greater on the Vey scale, occur on average once every 50 to 100,000 years. The last such event was the Toba supereruption in present-day Sumatra, approximately 74,000 years ago. The Toba eruption was so large that genetic evidence suggests it may have reduced the global human population to a few thousand breeding pairs, creating a population bottleneck that is still visible in the genome of every human being alive today. The volcanic field that produced Toba is still geologically active. The Yellowstone caldera in the western United States, source of 3 previous supereruptions in the past 2 million years, remains seismically alert. The Phlegraean fields beneath the city of Naples in Italy, source of a major eruption 9,000 years ago that may have contributed to the extinction of Neanderthals in Europe, has been showing signs of unrest in recent decades. None of these systems is imminently due to erupt, but all of them are reminders that the volcanic threat to human civilization is not, in geological terms, a remote one. I want to spend more time on the volcanic dimension, because the volcanic threat is in some ways the most underestimated of the major hazard categories we are discussing. Modern human civilization has, with very few exceptions, no living memory of a truly large volcanic eruption. The most recent Vey 6 event was the eruption of Mount Pinatubo in the Philippines in June 1991, an eruption that, while significant in its global climatic effects, was small by the standards of the historical record. The most recent Vey 7 event was the 1815 eruption of Mount Tambora, more than 200 years ago. The most recent Vey 8 event, by the standard chronology, was the Taup eruption in present-day New Zealand approximately 26,500 years ago. We are, in other words, living through an unusually quiet period in the global volcanic history, and the systems that produced the great eruptions of the past are, with very few exceptions, still present and still active beneath our feet. Consider the Campi Flegrei caldera complex in southern Italy. The complex occupies a region of approximately 150 square kilometres immediately west of the city of Naples, with parts of the active volcanic system extending beneath the metropolitan area itself. Approximately 350,000 people live directly above the caldera. Another 2 million live within 10 kilometers of its boundary. The system has produced two major eruptions in the past 40,000 years. The Campanian ignimbrite eruption of approximately 39,000 years ago, possibly the largest volcanic event in Europe in the past 200,000 years, and the Neapolitan yellow tuff eruption of approximately 15,000 years ago. Smaller than the Campanian ignimbrite, but still large enough to have shaped the geography and human settlement patterns of the entire region. In the centuries since these events, smaller eruptions have occurred at intervals of decades to centuries. The last eruption was in 1538, an event that created a new mountain, Monte Nuovo, in the course of a single week. Since that time, the caldera has been quiet, but not entirely silent. Episodes of ground uplift called bradyseismic events have occurred in the 1530s preceding the Monte Nuovo eruption, in the 1970s and 1980s, and again with increasing intensity since 2005. The most recent bradyseismic episode has produced cumulative ground uplift of more than a metre in some locations, accompanied by increasing seismic activity and changes in the chemistry of fumarole gases. Researchers monitoring the caldera have published, in the last several years, papers suggesting that the system may be approaching a critical state that could precede an eruptive event. The Italian civil protection authorities have updated their emergency plans. The evacuation procedures for the most vulnerable zones have been refined. But the actual population at risk, the actual exposure of one of the largest metropolitan areas in southern Europe to a potentially significant volcanic event, has not been meaningfully reduced. The Yellowstone caldera in the western United States is, in some ways, the most famous volcanic system in the world, and yet the actual risk it poses is widely misunderstood. The popular imagination, fed by documentaries and dramatic visualizations, tends to focus on the possibility of a super-eruption, a V8 event capable of devastating most of North America and altering global climate for years. Such an event is, in the very long run, possible. Yellowstone has produced 3 super-eruptions in the past 2 million years, with the most recent occurring approximately 640,000 years ago. The system is, on the long-time scales of geological processes, due for another major eruption. But the probability of a super-eruption in any given century, even in any given millennium, is extremely low. What is much more probable, and much less discussed, is a smaller event. A hydrothermal explosion, a lava flow within the existing caldera, a small phreatomagmatic eruption from one of the active geyser fields. These smaller events, while not civilization-threatening, can be locally devastating. The hydrothermal system at Yellowstone is enormous, with stored thermal energy sufficient to produce explosions on a scale comparable to large industrial accidents. The probability of such an event in the coming decades is not trivially small, and the consequences for the millions of annual visitors to the national park and for the local communities could be significant. The Phlegrain Fields and Yellowstone are just 2 examples among many. The Long Valley caldera in California, the Ira caldera in Japan, source of the eruption of Sakurajima and other smaller events, the Toba caldera in Sumatra, source of the largest known volcanic eruption of the past 2 million years, the Taupo volcanic zone in New Zealand, the Aso caldera in Japan, the Atitlan caldera in Guatemala. The list of large, active monitored caldera systems is dozens long. Most of them have been quiet for thousands of years. Some of them have been quiet for tens of thousands of years. None of them are extinct. All of them, in the long view, will erupt again. The question is when, where, and with what magnitude. And then there are the smaller volcanoes, the stratovolcanoes and shield volcanoes that, while incapable of producing the kind of super-eruption that the major calderas can produce, nonetheless pose significant local and regional hazards. Mount Vesuvius, the volcano that famously destroyed Pompeii and Herculaneum in 79 AD, remains an active system with a population of approximately 3 million people living within its immediate hazard zone. Mount Fuji in Japan, last erupted in 1707, sits within the densely populated Kanto Plain. Mount Rainier in Washington state, with a glacial cover that creates the potential for catastrophic lahars, dominates the skyline above Seattle and Tacoma. Popocatépetl outside Mexico City, periodically active, lies within sight of one of the largest metropolitan areas in the Western Hemisphere. Each of these systems, in some statistical sense, is overdue for a significant eruption. Each of them is well monitored. None of them is fully prepared for, in the sense of having the exposed population and infrastructure adequately removed from the most vulnerable zones. Quick reminder before we continue. If what you are hearing right now is the kind of analysis you want more of, hit the like button. It costs you nothing and it tells the algorithm to push this video to more people who need to hear it. And if you have not subscribed yet, this is your second chance. Subscribe and turn on the bell, because the data trail we are about to walk down in the next section is something almost nobody is connecting publicly, and I want you to be there when the next event drops. Like, subscribe, comment with the city you are watching from. Let us continue. Now we arrive at what I believe is the most important section of this entire video, because everything we have discussed so far, the solar storms, the historical earthquakes, the volcanic eruptions, the near-Earth objects, these have traditionally been studied as completely separate phenomena. Solar physicists do not, as a rule, talk to seismologists. Volcanologists do not, as a rule, talk to asteroid hunters. Each discipline has its own journals, its own conferences, its own funding streams, its own technical vocabulary. But in the last 15 years, a growing number of researchers from across these disciplines have begun, quietly, to publish work suggesting that the connections between these phenomena may be far stronger than the traditional siloed approach has allowed us to see. And what is emerging from that work is a picture that, if even partially correct, fundamentally changes how we should be thinking about the resilience of human civilization. Let me give you a concrete example. In 2012, a team led by the physicist Jeffrey Love at the United States Geological Survey published an analysis examining the correlation between large geomagnetic storms and changes in the rate of earthquakes. The traditional view in seismology has long been that solar activity has no measurable effect on the rate at which the Earth's tectonic plates release accumulated stress. Earthquakes are driven by plate motion. Plate motion is driven by mantle convection. Mantle convection has nothing to do with the sun. Case closed. Except, in the data, the case was not closed. Love and his collaborators found a small but statistically detectable correlation between major geomagnetic disturbances and a modest increase in the rate of moderate earthquakes in the following several days. The effect was small. The mechanism was and remains debated, but the correlation in the data was real, and it was just one of a growing number of such correlations that researchers were beginning to document. In 2014, a separate team working with data from the active volcanic eruption database examined whether the timing of volcanic eruptions showed any correlation with solar activity. Volcanoes, like earthquakes, are driven by deep earth processes that, on the face of it, should be entirely independent of the sun. Magma rises because of density differences in the mantle. Eruptions occur when accumulated gas pressure exceeds the strength of the overlying rock. The sun, 93 million miles away, should have nothing to do with any of it. And yet, the analysis found that the largest volcanic eruptions of the past 3 centuries showed a modest but statistically significant tendency to cluster around solar minima, the periods of lowest solar activity in the 11-year cycle. The proposed mechanism, controversial but not yet refuted, involves the modulation of cosmic ray flux by the solar magnetic field. During solar minima, more cosmic rays reach the Earth's surface and the upper layers of the crust. Those cosmic rays may, the hypothesis suggests, contribute to the nucleation of bubbles in magma chambers, accelerating the eruptive process. Speculative? Yes. Disproven? No. And then there is the work being done at multiple institutions on the relationship between the solar cycle and the rate of bolide impacts and near-Earth object encounters. The catalogue of detected near-Earth objects has grown explosively in the last 20 years, from roughly 500 known objects of size greater than 1 kilometre in 2000 to more than 25,000 objects of all sizes today. That growth is largely the result of improved detection capabilities, not an actual increase in the number of objects. But the catalogue has also revealed something that frankly was not entirely expected. The number of objects making close approaches to Earth, defined as approaches within 20 lunar distances, is high, not catastrophically high, but high enough that in any given year, multiple objects of the size that destroyed Tunguska in 1908 pass through Earth's orbital neighbourhood without striking us. Most of them are discovered, some of them are not, and every single one of them represents a reminder that the cosmos is not the empty, peaceful neighbourhood that our daily lives might suggest. The connections between these phenomena are not, in most cases, causal in any simple sense. The Sun does not cause earthquakes the way a fist causes a bruise. The orbital dynamics of asteroids are not, in any meaningful way, modulated by solar weather. But what is emerging from the cross-disciplinary work of the last 15 years is the recognition that we live on a planet, in a solar system, that is far more dynamic, far more interconnected, and far more capable of surprising us than the textbooks of our parents' generation acknowledged. The Sun is not stable, the Earth is not quiet, the cosmos is not empty. And the assumptions that have underpinned the design of our infrastructure, our cities, our institutions, and our daily lives have been built in many cases on a foundation of statistical samples too short to capture the full range of what nature is capable of throwing at us. Let me give you another example, one that is rarely discussed outside of specialist circles. The Schumann resonance is a set of electromagnetic frequencies that propagate in the cavity formed between the Earth's surface and the ionosphere. The fundamental frequency, around 83 Hz, has been measured continuously since the 1960s. For most of that period, the resonance was remarkably stable. The base frequency varied slightly with the daily cycle of solar illumination, with the 11-year solar cycle, and with the rate of global lightning activity. But the variations were small and predictable. Beginning in the early 2010s, however, multiple research groups began documenting larger and more unpredictable variations in the Schumann resonance, spikes in amplitude, shifts in the harmonic structure, episodes of unusual coherence. The mainstream interpretation is that these changes reflect the increased complexity of the ionosphere during the rising phase of solar cycle 25, combined with the increasing density of artificial electromagnetic emissions from human technology. But a minority view, increasingly difficult to dismiss as the data accumulates, suggests that we may be observing genuine, novel behaviour in the electromagnetic environment of our planet, the long-term implications of which we do not yet understand. And then there is what is happening with the Earth's magnetic field itself. The field is, on geological timescales, weakening. Over the last 200 years, it has lost roughly 10% of its overall strength. The rate of weakening appears to be accelerating in recent decades, with measurements from the European Space Agency's Swarm satellite constellation showing localized regions of even more rapid decline. The most prominent such region is the South Atlantic anomaly, a vast zone of reduced magnetic field strength over the southern Atlantic Ocean and South America, where satellites passing overhead are exposed to significantly higher radiation doses. The South Atlantic anomaly is growing. It is splitting. There is now evidence, based on swarm satellite data, that it is in the process of dividing into two separate cells, a structural change unprecedented in the period of direct satellite monitoring. What that change means, in terms of the long-term evolution of the magnetic field, is the subject of active scientific debate. Whether it portends a geomagnetic field reversal, a complete flip of magnetic north and south of the kind that the geological record shows has happened many times before, is unknown. What is known is that we are watching, in real time, a major structural change in the protective magnetic envelope that shields our planet from the worst of what space throws at us. The South Atlantic anomaly deserves more discussion, because it is one of the most actively changing features of our planet's environment, and one that almost no one in the general public has heard of. The anomaly is, in simple terms, a region where the strength of the Earth's magnetic field at the surface is much lower than the global average. The cause lies deep in the Earth's outer core, in the convective currents of liquid iron that generate the magnetic field. Specifically, the South Atlantic anomaly appears to be the surface expression of a region of reversed magnetic polarity within the outer core itself, a kind of bubble of opposite direction field that is pushed up against the core mantle boundary beneath the South Atlantic Ocean. The geometric effect of that reversed polarity region is to weaken the field at the surface above it, creating the anomaly we observe. Why does this matter? Because satellites passing over the anomaly are exposed to significantly higher levels of energetic charged particles than they encounter elsewhere in their orbits. The Van Allen radiation belts, the donut-shaped regions of trapped charged particles that surround the Earth, dip closer to the surface in the anomaly region. Satellites in low Earth orbit, normally well below the radiation belts, find themselves passing through the lower edge of the inner belt every time they cross the anomaly. The radiation dose accumulates, electronic components age more rapidly. Single event upsets become more frequent. Multiple major satellites, including the Hubble Space Telescope, are routinely powered down during their passages over the anomaly to protect sensitive instruments from radiation damage. The Hubble loses about 15% of its possible observing time to anomaly-related operational restrictions. And the anomaly is, by every measurement, growing larger and weakening further over time. The European Space Agency's Swarm mission, launched in 2013, consists of 3 satellites in carefully chosen orbits that map the structure and evolution of the geomagnetic field with unprecedented precision. The data from Swarm, combined with historical observations from older satellites and ground-based magnetic observatories, allows researchers to track the evolution of the field on timescales of months and years. What that data is showing, with increasing clarity, is that the South Atlantic anomaly is splitting into 2 distinct cells. One cell remains centered over the South Atlantic Ocean. The other is migrating westward, toward the South American continent. The implications of this split for the future evolution of the field and for the radiation environment of satellites in low Earth orbit are not yet fully understood. But the change is real. It is happening now. And it represents the kind of large-scale, observable, ongoing transformation of our planetary environment that, in any rational system of public communication, would be front-page news. Let us also address the question of geomagnetic field reversals. The Earth's magnetic field has, over the long history of the planet, repeatedly reversed its polarity. Magnetic north has become magnetic south, and vice versa, hundreds of times in the geological record. The reversals are recorded in the alignment of magnetic minerals in volcanic rocks of various ages, allowing researchers to map the history of the field with reasonable precision. What that record tells us is sobering. Reversals are irregular, occurring on average about once every 200 to 300,000 years, but with substantial variation. Some intervals between reversals are very short, perhaps tens of thousands of years. Others are very long, more than 10 million years. The last full reversal occurred approximately 780,000 years ago. By the average recurrence interval, we are, again, overdue, but here is where it gets genuinely interesting. The geological record also contains evidence of what are called geomagnetic excursions, events in which the field weakens dramatically, partial reversal occurs, but the field then recovers without completing the reversal. Excursions are more common than full reversals, occurring perhaps every 10 to 50,000 years on average. The most recent excursion, the Lachamps event, occurred approximately 42,000 years ago. During the Lachamps event, the strength of the magnetic field dropped to less than 10% of its current value for several centuries. The implications for the biosphere of that period are still being researched. Recent studies have suggested correlations between the Lachamps event and significant climate disruptions, biological extinctions, and the eventual disappearance of the Neanderthals from Europe. The causal links remain debated, but the timing is striking. What does all of this mean for us in the modern world? The honest answer is that we do not know. The current weakening of the field, if it continues at the present rate, could indicate the beginning of a reversal or an excursion, or it could indicate a temporary fluctuation that will reverse course in the coming decades. The timescales of these processes are long enough, and our period of direct observation short enough, that distinguishing between scenarios is genuinely difficult. What we can say is that the protective effect of the magnetic field against cosmic radiation, against solar particle events, against atmospheric loss to the solar wind, is being measurably reduced. And we can say that the systems that depend on the predictable behaviour of the magnetic field, including satellite operations, animal navigation, and certain aspects of human technology, are operating in an environment that is no longer fully predictable. The connections between these phenomena, then, may be less direct than the connection between cause and effect. They may instead be the kind of connection that exists in any complex system whose components are evolving simultaneously. The sun is changing. The geomagnetic field is changing. The geological stress patterns are changing. The orbital populations are changing. None of these changes is necessarily caused by the others in any narrow physical sense. But all of them are happening at the same time. All of them are happening on time scales that for the first time in human history we are able to measure with precision, and all of them are reshaping the environment in which our civilization is trying to maintain its stability. That is the deeper meaning of the connections we have been examining. Not that any one of them is the cause of any other, but that all of them, together, constitute a context within which our institutions, our infrastructures, and our assumptions must operate. And to navigate that context successfully, we need to look at it honestly. I want to spend the remainder of this section on the population of near-Earth objects, because the orbital neighbourhood we inhabit is far busier than most people realise, and the trends in that population are worth understanding in detail. As of the most recent catalogue updates, more than 35,000 near-Earth asteroids have been formally catalogued by the Minor Planet Center, the international clearinghouse for asteroid and comet observations operated by the Smithsonian Astrophysical Observatory under the auspices of the International Astronomical Union. Of those 35,000 objects, more than 10,000 are larger than 140 meters in diameter, the size threshold above which an impact would produce regional scale damage. More than 900 are larger than 1 kilometer, the size threshold above which an impact would produce global scale damage with significant effects on climate, agriculture, and human civilization. And approximately 20 are larger than 5 kilometers, the size threshold above which an impact would constitute an existential threat to the human species. The cataloguing effort has been remarkably successful for the largest objects. The estimated completeness of the catalogue for objects larger than 1 kilometre exceeds 95%. The remaining undiscovered objects in that size range are, by every available analysis, in orbits that are difficult to observe from ground-based telescopes, either because they spend most of their time on the daylight side of the Earth, or because their orbits are highly inclined and rarely bring them near the ecliptic plane where most surveys focus their attention. The Vera Rubin Observatory, with its survey scheduled to begin in the late 2020s, is expected to fill in many of the remaining gaps for kilometre-class objects. By the early 2030s, the catalogue of large near-Earth objects should be effectively complete, allowing planetary defence planners to confidently assess the threat from objects in that size range. The situation for smaller objects is much less reassuring. The estimated completeness of the catalogue for objects in the 140 metre to 1 kilometre range is between 50 and 60% as of the most recent assessments. That means somewhere between 4,000 and 6,000 undiscovered objects of this size are presently in orbits that bring them within striking distance of the Earth. The probability of any one of those objects impacting the Earth in any given year is, individually, very low. But the cumulative probability, integrated over the entire undiscovered population, is not trivial. The standard impact frequency curves, calibrated against the cratering record of the Earth and the Moon, suggest that an impact by a 140 metre or larger object occurs, on average, once every 5 to 10,000 years. The most recent such impact, the Tunguska event of June 30th, 1908, struck a remote region of Siberia and caused damage over an area of approximately 2,000 square kilometres. The energy released in the Tunguska event has been estimated at between 3 and 15 megatons, equivalent to between 200 and 1,000 of the bombs dropped on Hiroshima. The fact that this impact occurred in a region with essentially no human population was in the deepest sense an accident of geography. The same impact occurring over a major urban area would have killed millions. But here is where it gets genuinely alarming. Even the catalogue of objects we have discovered is in many cases less reassuring than the raw numbers suggest. The orbital determinations for many catalogued objects, particularly the smaller and more recently discovered ones, are based on relatively brief observation arcs. Over time, as the objects move along their orbits and additional observations are accumulated, the orbital parameters are refined. But in the period before that refinement is complete, the uncertainty in the future trajectory of an object can be substantial. Asteroids that initially appear to have safe orbits can, as their orbital determinations improve, be revealed to have higher impact probabilities than originally estimated. The reverse is also true. Objects that initially appear threatening can be shown through additional observation to have safe orbits. The process of orbital refinement is ongoing, continuous, and dependent on the availability of telescopic resources and the willingness of professional and amateur astronomers to devote time to the observations. One specific class of objects deserves particular attention. Comets, the icy remnants of the formation of the outer solar system, can on occasion be perturbed into orbits that bring them into the inner solar system on their way to a close encounter with the Sun. Long-period comets, those with orbital periods longer than 200 years, are particularly dangerous because they typically arrive without warning. The first sighting of a long-period comet often occurs only months before its closest approach. If such a comet were on a collision course with the Earth, the warning time would be measured in weeks to months, not in the years to decades that the asteroid catalogue provides for known threats. The impact velocity of a long-period comet, due to its highly elliptical orbit, can be much higher than the typical impact velocity of an asteroid. The resulting energy release for any given object size would be correspondingly larger. Fortunately, the rate of large long-period comet impacts is, on the long time scales of geological history, much lower than the rate of asteroid impacts. But the rate is not zero, and the absence of any meaningful early warning capability for long-period comets remains a significant gap in the planetary defense architecture. Beyond the natural population of asteroids and comets, there is the rapidly growing population of artificial objects in Earth orbit, the consequences of which are increasingly relevant to the broader discussion of space hazards. As of the most recent counts, more than 10,000 active satellites are operating in various orbits around the Earth. The number has more than tripled in the past 5 years, driven primarily by the deployment of large commercial constellations such as Starlink, OneWeb, and several others. In addition to the active satellites, more than 30,000 catalogued objects of debris, ranging from spent rocket stages to fragments produced by collisions and explosions, are in tracked orbits, and below the size threshold of routine tracking, an estimated several hundred million additional debris particles, each capable of disabling or destroying a spacecraft on impact, populate the orbital environment. The Kessler syndrome, named after the NASA scientist Donald Kessler, who first articulated the concept in 1978, describes a scenario in which the density of debris in low Earth orbit becomes high enough that collisions between debris objects generate additional debris faster than the orbital environment can naturally clean itself through atmospheric drag. The runaway cascade of collisions, in the worst case, could render large regions of low Earth orbit unusable for generations. We are not, by current assessments, in a Kessler runaway. But we are, by every available analysis, approaching the threshold conditions for one. The collision in 2009 between the operational Iridium-33 satellite and the defunct Russian Cosmos 2251 satellite produced more than 2,000 catalogued debris fragments, many of which are still in orbit and will remain so for decades. The Chinese anti-satellite test of 2007, which deliberately destroyed the defunct Fengyun 1C weather satellite, produced more than 3,000 additional debris fragments. Each major debris-generating event of this kind moves the orbital environment incrementally closer to the threshold at which natural collisional cascades begin to dominate the debris population, and the rapid expansion of active satellite numbers in the past several years has, by some estimates, increased the rate of close conjunction events, near misses requiring evasive maneuvering, by more than an order of magnitude relative to the levels of a decade ago. The intersection of space weather, asteroid hazards, and orbital debris is, in some ways, the defining challenge of the new era of space operations. Each of these threats, considered individually, is manageable with current technology and reasonable investment. Considered collectively, in the context of a satellite infrastructure that has become essential to the functioning of modern civilization, they constitute a category of risk for which the existing institutional, regulatory, and engineering responses are inadequate. The institutions responsible for space weather monitoring, asteroid hunting, and orbital debris management are, in most countries, organisationally separate from one another, with limited coordination and limited shared resources. The treatment of the orbital environment as a common resource, requiring international coordination and protection, has lagged significantly behind the operational reality of the increasing utilisation of that environment. And the public understanding of these issues, while gradually improving, remains far behind the actual state of affairs. So what does all of this mean? Let us bring the threads together. We have established that the Sun is in an active phase of its 11-year cycle, and that the current cycle, Solar Cycle 25, has consistently exceeded the official forecasts issued by the NOAA Space Weather Prediction Center and the International Consensus Panel. We have established that a single G5 storm, the May 2024 event, came uncomfortably close to causing major infrastructure damage, and that the world's escape from that storm was a matter of fortunate timing rather than fundamental resilience. We have established that the historical record contains storms substantially larger than anything modern infrastructure has been tested against. and that the probabilistic analysis of when the next such storm will occur is not reassuring. We have established that the seismic record shows long overdue great earthquakes on multiple major fault systems, including Cascadia, the Himalayan front, and several segments of the Pacific Ring of Fire. We have established that the volcanic record contains supereruptions far larger than any modern human civilization has had to manage. And we have established that the cosmos continues to deliver on a regular basis near-Earth objects of size sufficient to cause regional or even global devastation. Putting all of that together yields a picture that is, I think, fundamentally different from the picture most people walk around with in their heads. The picture most people have is that the world is, on the whole, predictable, that the systems that sustain modern life, electricity, water, food distribution, communications, finance, are robust, redundant, and resilient. That major disasters are rare, geographically bounded, and recoverable. That the institutions, governments, and infrastructures of the developed world have, by virtue of their sophistication, transcended the kinds of large-scale catastrophic vulnerabilities that defined human history before the modern era. Each one of those assumptions, on careful examination of the data we have just walked through, is at best partially true. At worst, dangerously false, but here is where it gets genuinely alarming. The vulnerability of modern infrastructure is not evenly distributed. Some systems are far more exposed than others. Electrical grids, particularly the high-voltage transmission backbones that carry power across continents, are the single most vulnerable element of the modern technological stack. The transformers that step voltage up and down at the boundaries of those transmission networks are custom-engineered, custom-built devices. The largest of them weigh hundreds of tons. They are built to order, with lead times measured in months to years. The global manufacturing capacity for high-voltage transformers is concentrated in a handful of facilities, most of them in Asia and Europe. A major geomagnetic storm that destroys, in a single event, even a small percentage of the high-voltage transformers in a developed nation could leave that nation without adequate electrical infrastructure for a period that would severely strain every other system that depends on electricity, which is, in the modern world, essentially every system. Satellites are the second great vulnerability. The number of active satellites in low Earth orbit has more than tripled in the last 5 years, driven primarily by the deployment of large commercial constellations. Those satellites perform critical functions: GPS positioning, global communications, weather forecasting, Earth observation, military reconnaissance, financial transaction timing, scientific research. The disabling of even a fraction of the active satellite fleet by a single major space weather event would have consequences that would ripple through every developed economy. We have seen previews of this. In February 2022, a minor geomagnetic storm, well below the threshold that would normally cause concern, caused the loss of 40 Starlink satellites within days of their launch. The heated and expanded upper atmosphere, swollen by the storm, caused atmospheric drag on the satellites at their initial low orbital altitude to exceed the limits the operators had planned for. The satellites deorbited. The event was, in the grand scheme of things, minor, but it was a clear signal of the fragility of orbital infrastructure in the face of space weather. The financial system is the third great vulnerability, and the one that is least appreciated by the general public. Modern financial transactions depend in ways that are not widely understood on precise time synchronization. The timestamps on trades, the clearing of transactions, the settlement of payments, all of these depend on the GPS time signal, which is distributed by the GPS satellite constellation. A disruption of GPS, whether by space weather, by satellite damage, or by other means, would cascade through the financial system in ways that would take days or weeks to resolve. Trades would fail to settle, payments would be delayed, ATMs would, in many cases, stop dispensing cash. The economic damage from a sustained GPS disruption is estimated in studies by the United States Department of Homeland Security to run into hundreds of billions of dollars per week. And GPS is fundamentally a space-based system. Every component of it is exposed to space weather. Every component of it depends on the continued functioning of equipment in geosynchronous orbit, 20,000 kilometers above the surface of the Earth, in a radiation environment that, during a major storm, can become hostile enough to permanently damage onboard electronics. The transportation system is the fourth major vulnerability. Modern commercial aviation depends on GPEs for navigation, on satellite communications for over-ocean and polar route operations, and on high-frequency radio as a backup. All three are exposed to space weather. During major storms, polar routes are routinely diverted to lower latitudes, adding flight time, increasing fuel consumption, and stressing the global aviation network. Maritime navigation depends similarly on GPs, with most large commercial vessels having largely retired their traditional celestial navigation capabilities decades ago. The disruption of GPs for an extended period would force a return to navigation methods that the current generation of maritime officers has in many cases never practiced. The transportation of food, fuel and manufactured goods that sustains modern urban populations would be severely affected. The food system is the fifth, and perhaps the most consequential, vulnerability. Modern industrial agriculture depends on GPS-guided machinery, on satellite-derived weather forecasting, on global communications for the coordination of supply chains, and on stable electrical infrastructure for the cooling, processing and distribution of perishable goods. The breakdown of any one of those systems, sustained over weeks, would result in significant disruptions to the food supply in major urban areas. The breakdown of all of them, sustained over months, would result in something that the developed world has not faced in generations. Genuine food insecurity. Real hunger. In populations that have, in many cases, lost the cultural and practical knowledge of how to grow, preserve, and prepare food without the intermediation of the industrial food system. This is not a hypothetical. It is the considered assessment of, among others, the United Kingdom's Royal Academy of Engineering, which published a major report in 2013 examining exactly this scenario. Now, none of this means that catastrophe is imminent. None of this means that you should be panicking. The probability of any given major event occurring in any given year is still relatively low. The number of redundancies and protective measures built into critical infrastructure is, in many cases, substantial. The capacity for human ingenuity and improvisation in the face of disruption has been demonstrated repeatedly in history. But the probability is not zero. The vulnerabilities are real. The cumulative trajectory of all the data we have walked through in this video is undeniably in the direction of greater exposure rather than less. And the gap between what could happen and what most people believe could happen is wide. Closing that gap, at least in your own mind, is one of the most valuable things you can do for yourself, for your family, for your community, and for your future. Let me also address something that often gets lost in discussions of these topics. The vulnerabilities I have outlined are real, but they are not deterministic. They are not destiny. Every one of them is the product of choices made by engineers, policymakers, and societies about how to design, build, and maintain the systems that sustain modern life. And every one of them can, in principle, be remediated by different choices made with the information we now possess about what could happen. The history of engineering is in many ways the history of learning from disasters. Bridges fell down, and we learned to build better bridges. Airplanes crashed, and we learned to build better airplanes. Power grids failed, and we learned to build, in some cases, better power grids. The question is whether we can learn from disasters before they happen. Whether we can use the data we have, the science we have, the historical record we have, to harden our systems against threats we have not yet experienced at their full magnitude. The answer to that question, as best I can determine from the published literature, is mixed. In some areas, real progress is being made. The North American Electric Reliability Corporation, the standards body for the North American power grid, has, in the years since the May 2024 storm, implemented updated requirements for the protection of high-voltage transformers against geomagnetically induced currents. The European Union has funded research programs aimed at improving space weather forecasting capabilities. The United States Geological Survey has expanded its monitoring of geomagnetic field variations across the continental United States, providing real-time data on the actual GIC environment during major storms. The international community has, through the International Telecommunication Union, developed standards for satellite hardening against space weather effects. None of these developments is by itself sufficient, but each one represents a step in the right direction. In other areas, progress has been disappointing. The replacement of aging high-voltage transformers, the single most expensive and most consequential element of grid hardening, proceeds at a glacial pace, dictated by depreciation schedules and budget cycles that have little to do with the actual risk environment. The development of a global network of space weather monitoring spacecraft, the kind of system that could provide multi-day advance warning of major events, has been repeatedly proposed and repeatedly underfunded. The integration of asteroid hunting into a comprehensive planetary defense program, the kind that the NASA Planetary Defense Coordination Office has been advocating for, has made progress but remains chronically resource constrained relative to the scale of the threat it is asked to address. The seismic and volcanic hazard mitigation efforts of most countries are vastly underfunded relative to the expected damages from the events they are intended to prevent. There is also, and this is perhaps the most important point of all, a fundamental challenge in motivating action on low probability, high consequence events. Human cognition is not well adapted to thinking about rare disasters. We tend to discount future risks. We tend to underweight the probability of events we have not personally experienced. We tend to focus our attention on the immediate and the visible, rather than the distant and the abstract. These cognitive biases are not flaws to be overcome through willpower. They are deep features of how the human brain processes risk, and they create a systematic challenge for the institutions that are tasked with managing risks on timescales longer than the political and economic cycles within which those institutions operate. The result is that, in nearly every domain we have discussed, the rational level of investment in resilience is substantially higher than the actual level of investment. This gap is not the result of incompetence or malice. It is a structural feature of how human societies allocate resources in the absence of immediate crisis. What can change this? History suggests that the most effective driver of large-scale investment in resilience is the experience of disaster. After the Halloween storms of 2003, NOAA's space weather monitoring capabilities were substantially upgraded. After the Tohoku earthquake and tsunami of 2011, Japan's tsunami protection and nuclear safety standards were significantly improved. After the Chelyabinsk meteor of 2013, NASA's planetary defense program received increased funding. Disaster, in other words, is the price we pay for the lessons we did not learn in advance. The challenge of our generation is to find ways to learn those lessons without paying that price. To use the science, the data, and the historical record to motivate the investments that we know, with the certainty available to us, will be needed. One area where we have collectively done a reasonable job is asteroid defense, and the lessons from that domain may be applicable elsewhere. In 1998, following the public attention generated by several near-miss events and the cultural impact of the films Armageddon and Deep Impact, the United States Congress directed NASA to identify 90% of near-Earth asteroids larger than 1 kilometer in diameter within 10 years. The deadline was missed, but the work continued. By 2010, the catalogue of 1 kilometer plus objects was substantially complete, and attention shifted to smaller objects. By 2022, NASA's DART mission had successfully demonstrated the kinetic impactor technique for asteroid deflection, hitting the asteroid Dimorphos and altering its orbital period by several percent. The Vera Rubin Observatory, scheduled to begin full operations in the late 2020s, is expected to discover the majority of near-Earth objects larger than 140 meters within the first few years of operation. None of this is enough. But the trajectory in this one domain is genuinely in the right direction. The combination of public attention, political will, scientific capability, and engineering demonstration has produced real progress. The question is whether comparable progress can be made in the other domains we have discussed. One dimension of the implications discussion that has not received adequate attention in either the popular or the academic literature is the question of cascading failures across coupled infrastructure systems. Modern civilization is not a collection of independent systems that happen to coexist. It is a tightly coupled, deeply interdependent network of systems, each of which depends on the continued functioning of multiple others. The power grid depends on natural gas pipelines for fuel. The natural gas pipelines depend on the power grid for compressor station operations. Water treatment depends on electricity. Sewage treatment depends on electricity. Hospital operations depend on electricity, water, communications, and supply chains. Communications depend on electricity, on data centers, and on satellite networks. Transportation depends on fuel supplies, on traffic management systems, and on GPS. Food distribution depends on transportation, on refrigeration, on electronic payment systems, and on communications. The list goes on, in increasingly complex patterns of mutual dependence. What this means in practical terms is that a disruption that takes out any single critical infrastructure system will, in nearly all realistic scenarios, propagate into adjacent systems within hours to days. A prolonged power outage produces a water outage when the treatment plants run out of backup fuel. A prolonged water outage produces a public health crisis as sanitation infrastructure fails. A prolonged communications outage produces a transportation crisis as logistics coordination breaks down. The failure modes of these coupled systems have been studied in academic and government settings for at least the past 2 decades. The general conclusion in the published literature is that the resilience of the integrated system is substantially lower than the resilience of any individual component. A failure cascade, once it begins, is very difficult to arrest. The recovery process in realistic models takes much longer than the initial disruption, because each subsystem must be brought back online in the proper sequence, with the proper testing and validation, before the next dependent subsystem can resume normal operations. But here is where it gets genuinely alarming. The standard assumption in infrastructure planning has long been that disruptions are local and short. A regional blackout lasting hours. A water main break lasting days. A flooded substation taking weeks to fully repair. The systems are designed, the procedures are written, the spare parts inventories are sized, all on the assumption that catastrophic events affect a limited geographic area and recover within a manageable time frame. The kinds of events we have been discussing in this video do not, in their worst manifestations, fit those assumptions. A Carrington-class geomagnetic storm could produce a continental scale grid disruption with a recovery time measured in months. A great earthquake on the Cascadia subduction zone could produce a regional disruption affecting a population of more than 10 million people for timescales much longer than the existing emergency response plans assume. A major volcanic eruption could produce global atmospheric effects lasting years. The mismatch between the planning assumptions and the realistic worst-case scenarios is one of the most important unaddressed problems in modern emergency management. There is, however, reason for measured optimism. The conversations I am describing are happening, in policy circles and in the relevant professional communities, at a level of seriousness that was not present even 10 years ago. The causal agency, established in the United States in the wake of the 2003 Halloween storms, has matured into a meaningful coordinating body for federal space weather activities. Similar institutions exist in Europe, Japan, and elsewhere. The international scientific community, through bodies like the International Living with a Star Programme and the International Council for Science, has expanded the scope and depth of cross-disciplinary collaboration. The private sector, particularly in the insurance and reinsurance industries, has begun systematically pricing the risks of major space weather and natural hazard events into actuarial models, which in turn drives investment in resilience measures by the entities that face the largest exposure. None of this is happening fast enough. But it is happening. The most encouraging trend, in my own assessment, is the increasing accessibility of the underlying data. 20 years ago, the kind of analysis I have presented in this video would have required access to specialized databases, technical software, and significant time investment. Today, much of the relevant data is publicly available through web portals operated by NOAA, NASA, USCS, ESA, JAXA, and other agencies. The barrier to entry for informed citizen engagement with these topics has dropped dramatically. The community of independent researchers, citizen scientists, and informed observers who follow these data in real time has grown correspondingly. The result is a kind of distributed early warning system, in which alerts and analysis propagate through social networks faster, in some cases, than through official channels. This is not, by itself, sufficient to address the underlying vulnerabilities, but it is a meaningful change in the cognitive landscape of public engagement with these issues. And it is, in the long run, one of the most important enabling conditions for the kind of broad-based response that the scale of the challenges actually requires. One final observation. The discussion of major hazards tends, by its nature, to focus on negative outcomes. Disasters, damage, casualties, disruption. This focus is appropriate in the sense that the practical purpose of hazard analysis is to motivate protective action. But it can be misleading, in the sense that it tends to obscure the remarkable progress that human civilization has made in reducing vulnerability to natural hazards over the past several centuries. Earthquake casualties per capita are dramatically lower in modern construction than in pre-modern construction. Tsunami warning systems have, in their relatively short history, almost certainly saved hundreds of thousands of lives. Volcanic eruptions that would have caused civilizational collapse in earlier eras now produce, in most cases, localized disruptions with measurable but manageable global effects. The hazard response capabilities of modern civilization, while imperfect, are far greater than those of any previous era. The challenge of the coming decades is not to create resilience from scratch, it is to extend, deepen, and apply the resilience capabilities we have already developed to threats that have, until now, been at the margin of public attention. That is a tractable challenge. It is a challenge we are capable of meeting. Whether we will meet it in time depends on choices we have not yet made. So, what can you actually do? Let me be very clear about this. The purpose of this video is not to leave you feeling helpless. The purpose is to give you, the viewer, a realistic and actionable understanding of the world we live in, so that you can make better decisions for yourself and the people you care about. Here is what I would suggest, in order of practicality and importance. First, develop a basic level of household resilience. This is not about becoming a prepper, in the cartoonish sense of the word. It is about thinking through, calmly and rationally, what your household would do if the electricity went out for a week. For 2 weeks. For a month. Do you have a reliable source of clean drinking water? Do you have enough non-perishable food to feed your family for 2 weeks without going to a store? Do you have a basic first aid kit, prescription medications, and the means to communicate with family members if cell service is down? Do you have cash on hand in case ATMs and electronic payment systems are not working? None of these preparations are expensive. None of them are unreasonable. They are, in fact, the same recommendations that every emergency management agency in every developed nation has been making, in dry official language, for decades. The Federal Emergency Management Agency in the United States, the Civil Contingency Secretariat in the United Kingdom, the Bundesamt for Bewegungsschutz in Germany. They all recommend 2 weeks of supplies. Very few households actually have them. Second, develop awareness. Subscribe to space weather alerts. The NOAA Space Weather Prediction Center publishes a free public alert system. The European Space Agency publishes similar information. There are smartphone apps that will notify you of major solar events. Knowing that a major storm is on the way, even by 24 hours, gives you the opportunity to charge devices, fill water containers, top off the gas tank, and avoid travel that could leave you stranded. Awareness is the cheapest and most effective form of resilience. Third, develop community. The single greatest predictor of how well a population recovers from a major disaster is the strength of local social ties. People who know their neighbours, people who participate in community organisations, people who have friends and family within a reasonable distance. These people recover faster, suffer less, and emerge stronger from disruptions than people who live in social isolation. This is not a recommendation about disaster preparedness. It is a recommendation about how to live a good life. But it also happens to be, by every measurable index, the single most important factor in real-world resilience to the kinds of large-scale events we have been discussing. Fourth, develop perspective. The cosmos is dynamic. The Earth is dynamic. The Sun is dynamic. None of this is new. None of this is unique to our era. Human beings have lived on this planet, under this sun, in this cosmos, for hundreds of thousands of years. They have lived through ice ages, through volcanic winters, through supernovae visible in daylight, through asteroid impacts large and small. Our species is here today not because our environment was gentle, but because our species was resilient. The capacity for resilience is in us. It is in every one of you watching this video. The events we have been discussing are not, in any meaningful sense, the end of the world. They are the world, doing what the world has always done. And the appropriate response is not fear. It is preparation, awareness, community, and perspective. With those 4 things, you can face whatever comes with clarity and with confidence. Fifth, and finally, support the work of the scientists and engineers who are, every day, building our collective understanding of these phenomena. The space weather monitoring infrastructure of the developed world is funded by your taxes. The seismologists and volcanologists who track the dynamic Earth are employed by your universities and your government agencies. The asteroid hunters who scan the skies for incoming objects are funded by NASA, by ESA, by JAXA, by ISRO, and by a growing number of private and philanthropic initiatives. This work is not, by global standards, expensive, but it is chronically underfunded relative to its actual importance. When you vote, when you advocate, when you talk to your elected representatives, mention this. The investment in monitoring, in forecasting, in resilience is among the highest leverage uses of public funding in the entire portfolio of government activity, because the cost of being warned about a major event in advance is almost always vastly less than the cost of being surprised by it. Let me get more specific about practical preparation, because the general advice I have given so far is necessary but not sufficient. The kinds of events we have been discussing have distinct preparation profiles. A solar storm-induced blackout is different from an earthquake, which is different from a volcanic eruption, which is different from a near-Earth object impact. The general principles of household resilience apply to all of them, but the specific preparations diverge in important ways. For solar storm preparedness, the most important consideration is electricity. A major geomagnetic storm could, in the worst case, cause widespread and prolonged power outages. Your household preparation should include, at minimum, a method of charging essential devices that does not depend on the grid. A small solar panel and a battery pack, capable of charging phones and small electronics, costs less than $200 and provides genuine resilience. A larger inverter generator, capable of powering a refrigerator and basic lighting, costs around $1,000 and is, for households that can afford it, a worthwhile investment. Beyond electricity, the considerations are the same as for any prolonged disruption. Water, food, medications, cash, communication plans, documents stored in protected formats. None of this is exotic. All of it is recommended by federal emergency management agencies. Very few households actually do it. For earthquake preparedness, the considerations shift somewhat. The immediate threat is structural. Your house, if it is not engineered for the seismic environment of your region, may not survive a major event without significant damage. Retrofitting an existing home for earthquake safety is expensive, but in high-risk regions, a worthwhile investment. Within the home, basic measures like securing tall furniture to the wall, installing latches on cabinets, and keeping shoes and a flashlight beside the bed are nearly free and dramatically reduce the risk of injury during a moderate shaking event. The longer-term considerations are similar to other disasters. Stored water. Stored food. The ability to communicate with family and to navigate disrupted infrastructure for the period required for emergency services to fully respond. In a major earthquake, that period may be longer than you expect. The Federal Emergency Management Agency recommends 2 weeks of self-sufficiency for residents of high-risk seismic regions. The actual response time for utilities to be fully restored may be weeks to months. For volcanic preparedness, the most important consideration is, paradoxically, location. If you do not live within the immediate hazard zone of an active volcano, your direct exposure to a volcanic eruption is limited. The indirect effects, however, can be significant even at substantial distances. Ashfall can disrupt air travel, contaminate water supplies, and damage agricultural production over thousands of kilometres. The 2010 eruption of Eyjafjallajökull in Iceland, a relatively small event, disrupted air travel across Europe for weeks. A larger eruption anywhere on the planet could have global economic consequences. The household preparation for these indirect effects overlaps substantially with the preparation for other disasters. Stored food and water, cash, communications, the ability to operate without immediate access to retail supplies. The same kit, with minor modifications, works for multiple disaster types. For near-Earth object preparedness, the considerations are different. The probability of a significant impact in any given year is very low, but the consequences of a major impact would be civilization scale. The honest answer for most households is that there is little practical preparation that you can do beyond the general resilience measures already discussed that would meaningfully affect your outcomes in a major impact event. The work of preventing such events is, in essence, a public good, requiring international coordination and substantial public investment. What you can do as an individual is to support the institutions and the funding that make that work possible. Advocacy for planetary defence funding, attention to the science, and engagement with the political process that determines how public resources are allocated. These are not glamorous activities, but they are, at the population level, the highest leverage activities you can engage in. Beyond the specific disaster scenarios, I want to emphasise one more time the importance of community. The single greatest predictor of resilience in the face of large-scale disruption is the strength of local social networks. People who know their neighbours, people who participate in community organisations, people who have friends and family within a reasonable distance. These people recover faster, suffer less, and emerge stronger from disruptions than people who live in social isolation. In an era when social isolation is, by every available measure, increasing across the developed world, this consideration is not just a recommendation about disaster preparedness. It is a recommendation about how to live a meaningful, resilient, and rewarding life. The investments you make in your relationships, in your community, in the people around you, are the investments that pay the largest dividends in any future scenario, good or bad. 3.3. Conclusion and final CTA 800. 1,000 words. We have covered a tremendous amount of ground in this video. We have walked through the science of the sun, the mechanics of solar flares and coronal mass ejections, the history of major space weather events, the seismic and volcanic record of our planet, the population of near-Earth objects, the connections between these phenomena, and the implications for the infrastructure that sustains modern civilization. If you have stayed with me this far, you now possess a level of understanding of these topics that, I am willing to say without exaggeration, places you in the top fraction of 1% of the global population. The data is publicly available. The science is, in most cases, settled. What is missing, almost everywhere, is the willingness to look at the data honestly, follow it where it leads, and integrate it into a coherent picture of the world we actually live in. That is the work this channel exists to do. Not to scare you, not to entertain you with apocalyptic fantasies, but to take the boring, difficult, important data published by the world's leading scientific agencies and to translate it into something that any thoughtful human being can understand and act on. The Sun is in the active phase of its 11-year cycle, and the cycle is running stronger than the consensus forecasts predicted. The geological record is reminding us that the quiet century we have lived through is not the historical norm. The cosmic neighbourhood is busier than the textbooks of 50 years ago suggested, and the infrastructure that sustains modern life is, in critical places, more fragile than the public understanding acknowledges. These are facts. You can verify them yourself. The links to the primary sources are in the description of this video. The data is one search away. The truth is available to anyone who wants to find it. If this video has been valuable to you, please do 4 things. First, hit the like button. It costs you nothing and it tells YouTube to push this content to other people who would benefit from hearing it. Second, share this video with one person in your life who you think would appreciate this perspective. One share. One person. That is how a community grows. Third, if you have not already subscribed, subscribe now and turn on the notification bell, because the events we are tracking on this channel are accelerating, and you want to be among the first to know when the next major story breaks. And fourth, leave a comment below. Tell me where you are watching from. Tell me what you thought. Tell me what topic you want covered next. I read every comment, and the questions that come in from you, the audience, directly shape what we cover in the months ahead. Stay aware, stay prepared, stay connected to the people you love, and stay tuned to this channel. Because the story we are telling here is not over. It is, in many ways, just beginning. Thank you for your time. Thank you for your attention. Thank you for caring enough about the truth to spend 2 hours of your life on a subject this important. I will see you in the next video. Before we close, there is one more dimension of the broader picture worth touching on, and that is the long-term trajectory of the conversation we are having. 25 years ago, the topics covered in this video were the province of a relatively small community of specialists: solar physicists, seismologists, volcanologists, astrobiologists, the general public had limited access to the underlying data, limited understanding of the relevant science, and limited motivation to engage with phenomena that seemed remote from daily life. In the intervening decades, that situation has changed dramatically. The data has become publicly accessible. The science has matured into a set of well-developed disciplines with mature predictive capabilities, and the events themselves, the May 2024 storm, the Tohoku earthquake, the Chelyabinsk meteor, the COVID-19 pandemic, have collectively demonstrated to the public that the world is more dynamic, more interconnected, and more capable of surprising us than the assumptions of late 20th century civilization tended to acknowledge. This shift in public consciousness is, in my view, one of the most important developments of our era. It is not, by itself, sufficient to address the underlying challenges, but it is a necessary precondition for any meaningful response. The institutions that allocate resources, the political processes that set priorities, the cultural norms that determine what is considered serious and what is considered fringe, all of these are downstream of the broader societal understanding of what is at stake. As that understanding improves, slowly, unevenly, but persistently, the conditions for serious action improve as well. The challenge for those of us who follow these topics, who care about them, who believe they matter, is to contribute to that improving understanding in a way that is honest, accurate, calibrated, and useful, to resist the temptation towards sensationalism that distorts the actual risk picture, to resist the temptation toward complacency that dismisses real threats, to occupy, in other words, the genuinely difficult cognitive territory of someone trying to see clearly in a domain where clear seeing is hard. One final thought before we close. The story I have told you in this video is in some ways a story about uncertainty, about the limits of what we can predict, about the gap between what we know and what we can know, about the way large, slow, powerful forces shape the world we live in, often without our awareness. But it is also, in a deeper sense, a story about agency, about the choices we make, individually and collectively, in the face of that uncertainty, about the ways we can, with attention and effort and good information, prepare ourselves to navigate whatever comes. The data we have walked through is real, the science is solid, the historical record is clear. The institutions that monitor these phenomena, despite chronic underfunding and political headwinds, do real work and produce real information. The forecasters at NOAA, the seismologists at USGS, the volcanologists at the various national observatories, the asteroid hunters at the international survey programs. These people are doing work that in a more rational allocation of public attention would be celebrated. They are not celebrated. They are, in most cases, anonymous, but they are, in a very direct sense, doing the work that keeps our civilization functional in the face of phenomena far older and far more powerful than our civilization itself. What you can do, beyond the practical preparations I have already outlined, is to value that work, to pay attention to it, to support it, through your votes, through your advocacy, through your engagement with the institutions that do it, to share what you have learned with the people in your life in the spirit of accurate information rather than fear. The world we live in is more interesting, more dynamic, and more consequential than the world that most people imagine. Knowing that, and acting on it with clarity rather than anxiety, is, in my view, one of the most valuable orientations you can adopt. It is the orientation of someone who takes the universe seriously. It is the orientation of someone who is, in the deepest sense, an adult about reality. I will close with this. The events we have been discussing, the solar storms, the earthquakes, the volcanic eruptions, the near-Earth objects, are not new. They are not invented by modern media. They are not the product of recent changes in the natural world. They are, in the largest sense, just what the universe does. They have been happening for billions of years. They will continue happening, in some form, for billions of years to come. What is new, in the cosmic scale of things, is us, the observers, the instruments, the interconnected, electricity-dependent, satellite-orbiting, GPS navigating, information processing civilization that has, in the last 150 years, transformed the surface of the planet and begun to extend into the cosmos beyond it. We are the new variable in this equation. The dynamic Earth, the dynamic Sun, the dynamic cosmos have been here all along. The question is what kind of civilization we choose to build, in the knowledge that those dynamics are real, and in the face of the choices they impose upon us. I believe we can build, are capable of building, are in some places already building, a civilization equal to those challenges. Whether we will, on the whole and in time, remains to be seen. That is the work. That is the story. That is the truth, as best I can determine it from the published record. Thank you for joining me on this journey. Thank you for caring enough about the truth to spend this much time on a subject this important. If you have not already, like the video, subscribe to the channel, share it with one person, and leave a comment with the city you are watching from. We will see each other again in the next video, in the next story, in the next chapter of what is, undeniably, an extraordinary time to be alive. Stay aware, stay prepared, stay connected. And until next time, this has been your space weather and Earth Dynamics briefing.